let us now look in a little more detail what the properties, quantifiable physical properties of different galaxies are. And the first question is, what can we measure? And we can use photometry or imaging and quantify in some way how much light is there as a, say, function of radius in different filters, say. We can also measure their metallicity or stellar populations as a function of spatial distribution. We can determine kinematics through Doppler shifts of rotational motions or just random motions that puff up the absorption lines. And those have to be put into some context. It's impossible to invert these measurements and derive model directly from them. There's just not enough information. Instead of that, we make reasonably conceived models of galaxy evolution, both dynamical and stellar evolution, see what they would predict in terms of observable properties, and then compare that with what's actually observed. And that seems to work actually very well. Now, the distribution of light is the simplest thing to answer, and since they're all centrally symmetric, it's the radial distribution of light. And for spiral galaxies, well, there are two components. There is a bulge in the middle, and then there is a disk. The disks themselves are exponential, just like in Milky Way. That's a semi-log plot, so straight line is the exponential. And you can see that in the outer parts, it's just that. And then you have an extra component in the middle, which is the bulge, which is like a little elliptical. Now, if you look in gas, you see some similarities and some differences. This is contours of the density of neutral hydrogen superposed in a visible light picture of this galaxy. And you can see gas extends much further out than stars. And this is generally the case. So we think what happens is that galaxies get built up in terms of stars from inside out. Most of early star formation happens for the bulge, and then the disk, and then disk keeps growing, and there is still plenty of hydrogen left in the outer radii to provide for star formation. On the other hand, if you look at dense gas, like molecular gas, you find out that it follows up spiral arms very nicely. And this is, again, not a great surprise because spiral arms, by compressing gas, is what stimulates a lot of star formation in the disks. But these are just images taken in the lines of molecular hydrogen or carbon dioxide or carbon monoxide. Now, what about elliptical galaxies and by same token bulges? Well, they're not exponential. They're fit with this funny formula, which is exponential of radius to 1/4 power. And that's due to an astronomer named Gerard de Vaucouleurs. And I think he came up upon this purely by experimenting to see what will work. Now, there is a more general formula that reduces to this one, but this tends to be the one that fits a lot of elliptical galaxies fairly well. The two plots, one is the log-log diagram, so power law will be a straight line. The one on the right is log brightness versus radius to the 1/4 power. And that gives you a straight line. This is where this came from. Why this particular profile? Oh, nobody knows. For that matter, we don't really know why the disk galaxies are exponential. They just are. These are standard dynamical forms that galaxies assume, and they don't come in any other flavors. And understanding why this is the case is going to be one of very interesting things to figure out in the future. Well, what about their shapes? The shapes would clearly depend from what side you look at them. And so the observed distribution of ellipticity peaks around 0.2, 0.3, so it's just slightly flattened. But you don't know whether you're looking at an oblate ellipsoid that's tilted, or a prolate one that's elongated, or something in between. And it turns out that actually elliptical galaxies are triaxial. They have different flattening in the three orthogonal axes, and or they could be spherical. Now, the reason for this is interesting. It's not that they're flattened by rotation, which is what you naively assume, which is what people assumed early on, that elliptical galaxies are just flattened by rotation, by centrifugal force. No. They're flattened, or rather their shapes are given by anisotropic velocity dispersion. This may look a little strange. Now, like pressure of gas in this room, you don't feel it different when you look north versus west. And yet, this is exactly what happens with gas of stars in an elliptical galaxy. So there is nothing to prevent this from happening. You have independent dynamics, if you will, in each of the orthogonal directions. And so you could, and you do, get different amounts of random motion in the three orthogonal directions. So in the direction we have the highest velocity dispersion of stars, they'll go furthest out, and those will be the longest axes. The one we have the least amount of motion will be the shortest axis, and there'll be one in between. And so they're not grossly triaxial, but they're just slightly triaxial, and dynamical measurements confirm this. One interesting thing is that those that are bigger tend to be more anisotropic. Now, understanding of this is that a lot of ellipticals form or grow by accreting outer galaxies. So if you, say, have, to begin, spherical elliptical galaxy, and you drop another galaxy in from some direction, it gets eventually absorbed, but that has brought kinetic energy that kind of prefers that particular direction of the impact. And so you'll end up with a stellar system that's a little elongated because we'll have a little extra random motion along that particular axis. All right, do this a million times. And so these incoming galaxies come from any odd direction. And depending from which direction you get more impacts, that's the one you're going to develop the largest velocity dispersion. So it makes sense that the biggest ones that have eaten most galaxies would have the largest anisotropies. And what about masses? We talked about massive spirals and flat rotation curves. For ellipticals, we don't have rotation curves. That doesn't matter, really, but use random motions of stars or gravitational lensing. And if you plot mass of stars on y-axis versus total mass, dynamical mass inferred from measurements of velocities, they correlate, all right, but in a tilted fashion, in the sense that more massive galaxies have larger fraction of the dark matter. And that means the smaller ones were more efficient in converting gas into stars while they could. And finally, dwarf galaxies. I mentioned that they're really a very different kind of beast, and most notably, they're very different in their mean densities. So these two plots show three different families of what we call hot stellar systems: globular star clusters, which are here really just for symmetry's sake, regular ellipticals, and those dwarf spheroidals. And you can see on these correlations of, say, radius versus projected density, or projected density versus luminosity, they sit in a very different parts of that parameter space. And they have even correlations of some sort, which are product of their physics. So that tells us right away that these are really very different kinds of objects. Now, for so-called dwarf elliptical galaxies, you can look at, say, some common luminosity and compare their mean densities. And it turns out the mean density between your typical dwarf elliptical and regular elliptical is roughly like between air and uranium, something like 4 orders of magnitude. And so calling them dwarf ellipticals is like using cotton puffs and calling them dwarf cannonballs. And so they really are very different kind of objects.